So we all talk about the fact of working on your thesis, but this is the best part of the thesis. If everyone can do the thesis in 3 minutes, you need none of them in school. You can get out of here. So it's kind of neat. You're going to think about this. We're going to do a presentation in 3 minutes, describe all your research, and get us to win this competition. We want to actually get to a point where you say, okay, I would buy this, right? You have to sell your thesis. I'm going to buy this thesis. It's incredible. So what these guys are going to do in their 3 minutes is basically the elevator pitch for the thesis. When I was in Boston, I was at a convention, and I went out in the elevator, and this guy with his brown trench coat comes up to the elevator with me. The door shuts, I press the button, and he says, hey, are you looking for a high-tech job somewhere? And I had this like 10-second, elevator pitch to him as he goes, as we go to the next floor. But they're actually hunting for different people. So the people that are presenting today are going to pitch what their thesis is. There are certain rules to this. In the rules, it's only 3 minutes. They can't go after 3 minutes. If they go after 3 minutes, they're disqualified. At the 2-minute mark, there will be a buzzer. And the timer is right in front of us here. And basically, they have then 60 seconds to finish. After they stop, they say thank you very much. We will have a 3-minute question and answer period per person. Any questions on the rules? All right.
ها؟ بالبركة أيوة مبروك أنا ما
check.
So first up, we have Suri Hadith Ravidan, and he's going to speak on underwater wireless energy transfer.
Thank you, ma'am. Good afternoon to one and all. Hope you enjoyed a refreshment break. So myself, Sri Raghu Padiyat Ravindra, under UW Stream Lab, directed by Dr. Ruske, and my thesis topic is underwater wireless energy transfer using MI-link, magneto-inductive link. So before going on with the topic, I want to talk brief about wired and wireless transmission. So an example, we all know about wired transmission at the Gulf of Mexico, the horizon which happened, disaster, so all the wired and everything was damaged. So moving on with wireless, we have like less of cost in maintenance and deployment. So moving on with MI system, magneto-inductive system, it's less immune to acoustic noises and temperature pressures when compared with acoustic communications and with optical communication or EM waves. So my thesis objective would be like most precisely on the short-range wireless communication for the MI and design of a 3D coil and the test measurements over air, freshwater and underwater seawater. And system, and I'm working on the transmitter front end for the effective transmission and the reception towards it. So the main methodology is considered as like you can see here in the block, like the desired power and data is delivered through an inductor coil which is in the transmitter, which produces a magnetic flux which is magnetically coupled over the receiver coil, and this flux generates voltage across the receiver. It's very simple. And this voltage can be rectified and regulated for another charging applications. So So around last year October, we have presented a prototype in the Dalhousie Strategic Fund announcement, and it was quite a success. And then we moved on with, it's about a single coil measurements. And we moved on with a design course where we designed FSK system using MI, designed for two frequencies, one is 90 kHz and 120 kHz. So my conclusion and future work would be precisely on three-dimensional coil, since it's sensitive to direction. So I'll be working on like all three-dimensional, like orthogonal planes, and moving on with the transmitter. So we'll be implemented on FPGA board where the binary information will be encoded using a QPSK module, and 3 power amplifiers will be included for each coils. Thank you.
Excellent, excellent. So, now, any questions? Dr. Chen.
So what frequency you are using?
For the design project, we used like 90 and 120 kilohertz.
Why use so low frequency?
For underwater, we need for MI system for low frequencies because our power amp is not capable of going higher frequencies. So I'm working on the three-dimensional coil for the better frequencies now.
Can we go higher frequency?
At this point, no.
Why?
Because we have a lot of issues.
What issues?
So I have to check the front end and the filter issues. So the power amplifier which we are working on was an evaluation kit. So it doesn't give us like enough power, enough range. And also certain coil measurements we have to do.
Is that related to your underwater?
Yeah, it's related.
It's just because the medium you're choosing for is salt water, so.
Yeah, so salinity is also a major cause, and also a depth because we have coupling losses.
So lower frequency, what happens? Lower frequency, what will happen for the transmission?
Lower frequencies, we have transmission loss. So we didn't test the one in the sea water yet. So it's just airborne. So the FSK signal which we did is airborne. So now we are implementing it slowly towards seawater. So it's under measurement.
Well, basically in the seawater, lower frequency, the distance you can transmit over is larger. That's why you lose low frequency.
Low frequency. Thank you, sir.
We have another question up here.
Hello. Have you considered any of the issues with the fact that you'll be in the ocean or in a lake and there's going to be crustaceans or other marine life buildup around it that will probably insulate or degrade your signals?
It's a wonderful question. Thank you. Yes, we take into consideration because if you choose lots of current and yes, it's going to affect the marine life, but we work on a low frequency and low power, which is below 1 amp. That's what we are working on. So it doesn't affect much of marine life as we tested in Dalhousie aquatron last year with few fishes around. So it's not making any effect with the fishes, and the condition was safe. But we didn't test it with lake or seawater yet.
But what I mean is also like you have things grow on. Any structure you put underwater is going to be grow on. There's going to be mussels. There's going to be algae or seaweed. It's going to be crawling. They're going to grow all over it. How will that affect your signals and conduction between the two systems?
Okay, so how the MI system going to work is, it's like when you induce like a certain frequency or like a current to it, the coil generates a magnetic flux. So it acts as a magnet. So that won't have much effect on the marine as far as we limit our frequency and current.
But what about marine's effect on your system?
Marines affect the system? No, it's perfectly insulated. So we have like a glued and it's perfectly insulated, so it won't affect our system. So it's like water won't come in, or like we have like a perfect sealing. So
Will detune the antenna? Will the change in the system because you have fouling cause your magnetic flux and the transference to change?
I'm sorry, I didn't quite get that. I'm sorry.
So when you have a buildup on a system, will that cause your system to no longer be tuned? Like, it's going to change how your electrical currents, like,
Little. Like when it's compared with seawater, yes, little is going to change, but I don't see much changes when work in the like a water which is in aquatron.
Any other questions?
My question about the distance between the center and the receiver under the water. What did you achieve?
So in Dalhousie aquatron, we achieved almost 6 to 8 meters, but it's a smaller coil setup, and we are limited to the evaluation boards and things like that. And for the FSK signal, like we transmitted almost, like for the airborne, almost I would say like 3 to 4 meters so far. So it's like very small coil setup, but you can see the coil here, like a orthogonal plane, 3-dimensional one. So I'm pretty sure like it's very big. It's like this big coil. So probably the range I'm looking between 10 meters to 20 meters.
All right, thank you very much. Can we have a round of applause? Next up, we have Sana Ramadan, and her presentation is on underwater communication through magnetic induction. So we'll give her a minute to get ready here, and I'll help with the microphone. There she goes. All right, so you start the call.
Hi everyone, today I'm going to talk about underwater communication through magnetic induction. So I will start with the introduction. Wireless underwater communication have been drawing attention for many research due to the obvious application underwater, such as in navigation, mine detection, and in pollution monitoring. However, underwater environment forces a great challenge in terms of reliable and real-time communication. So, magnetic induction is a promising solution for underwater communication for the near field. So, at the end of our study, the proposed work offers a guideline for the design in terms of data loss, capacity, data rate, and the bandwidth. So, also communication through a conductive media such as seawater is only possible over a distance of a few skin depths, because the skin depth is equal to a square root of 2 over omega mu sigma. Here we have the sigma is equal to 4 S over m. So the communication will be considering in the near field where the T less than 1. We have here some results, and we have the discussion. So we calculated the attenuation rate by considering both the cubic distance attenuation and exponential attenuation. Also, the figure 1 shows the attenuation of an MI channel as a function of a frequency and the distance. So as we can see here in the figure, a few hundred meters can be achieved for low frequency. As in the figure 2, the relation between the values and the distance. So for the distance close to MI channel or MI source, larger change in the values will considering. However, for distance far away from MI channel, small change in the loss will be experienced. And finally, we calculate the induced voltage by Faraday's law as a function of frequency, distance, and parameters. So here in the figure, as we can see, it is a bandpass behavior is seen because of interplay between Faraday's induction of law and exponential attenuation. In conclusion, by the end of our research, we roughly estimated the achievable range, bandwidth, and the capacity. For the further research, in our research, we focus just on the medium issue, so it is recommended to take into account the characteristic of the coil and transceiver. Also, the MI channel noise is demonstrated by theoretical research, so it is recommended to take into account to measure by newer and more accurate techniques. And here we have our reference. Thank you for listening.
Excellent, excellent. All right, so now, any questions? Come on, you have to have a good question.
I have the same question. Why you use magnetic inductions for underwater?
Because it is a good way or good techniques for underwater, but just for the short range. So it's more reliable for the real and real time.
Can I use a radio wave?
Yeah, you can use a lot of the problem and challenge over there. It's like reflection and more attenuation and propagation delay.
In the sea underwater?
Yeah, it is in the sea and water.
You probably don't. You cannot use one.
Because it's considering as a conductor medium, and it is for the short range, we can achieve like up to 1 meters.
No, a radio wave in the high frequency underwater is happening here. So.
Yeah, but I will use here low frequency.
So that's why I use magnetic inductions, which is low frequency.
Yeah.
Okay, excellent question. So, other questions? All right, here we have one.
Actually, I wanted to ask you about, did you find any optimal frequency for, which is a function of depth?
Yeah, it is 70 kilohertz.
70 kilohertz?
Yeah.
And did you find a channel capacity for this?
It is not yet.
Just, but how about the channel bandwidth? Did you?
Yeah, it is considered with the channel capacity. Channel capacity and bandwidth are working now together to find the results from them.
What kind of signal did you transfer between your RSTs?
Fetch key. BSK. BSK.
Okay, BSK?
Yeah.
Thank you much.
Do we have time for one more question? No? Does anyone have a question? All right, fair.
My question is about the losses versus the frequency, the relation between the frequency and the power losses.
Yeah, it is the inverse.
Is it linear or non-linear or what?
It is like the inverse of rotation. For the high frequency, it is linear. For the high frequency, it will be high to attenuation and high values.
And this one sort of leads to the same questions about the optimal frequency for that can be achieved, so
Yeah.
that the losses will be the lowest point.
It is right now it is 70 kilohertz.
And it depends also on the kind of water. So.
Yeah, because it is seawater and is considering as a good conductor because it is high. Has high conductivity, so it is almost too high.
So this optimal frequency will be not fixed for one spot of water, and for example, for one area, the solid.
No, but for the seawater, it's
Depends on
considering
the
as
level of.
the same conductivity. I assume it's almost the same conductivity. It is almost 4 over 8.
Thank you.
All right, let's have a round of applause for Sana. So next we have Jia Chang Gao.
Hi.
Gao, okay. And he's going to speak on indoor radio tracking system. Okay, ready?
Yeah, I'm good.
Start.
Hello everyone, my name is Joshua Guo and my supervisor is David Chen. My topic is indoor radio tracking system. As you may know, there are two conventional methods in indoor tracking. The first one is called RF localization system, which use Wi-Fi and other communication devices to track the target. And the other one is called Kinect, which is kind of gaming devices. And compared with these two conventional methods, our system has two advantages. Because our system uses radio reflection signal to track the target, so it doesn't require users to carry any wireless devices. And it also doesn't require users to stay within the device's line of sight. So in a word, our system is much more convenient and friendly than these two conventional methods. And there are a few future applications for our system. The most important one is called smart house. And imagine that you stay in a house with such system. And for example, if you want to turn on TV, all you need to do is just to point out to the TV, and then the system can detect such motion and then turn on the TV automatically for you. And another important application is called fall detection, which is kind of a security application. And for the second part, I want to introduce some methodologies used in our system. The first one is how to calculate this TOI, which is the time of flight of the transmitted signal. Because we know the distance between the target and the indoor target and the antenna is pretty short. Therefore, the delay between the transmitted signal and the receiving signal is pretty small in time domain, makes it hard to detect directly. Therefore, we introduce a method called FMCW, which is frequency modulated carrier wave. For FMCW, the frequency of the transmitted signal changes linearly as time goes by. Therefore, instead of trying to calculate this TOF directly, we try to observe this frequency shift in frequency domain and then use this frequency shift to calculate this TOF. It's much more easier because the frequency shift in frequency domain is much bigger than the delay in time domain. And the second one is I want to introduce how to locate the target. And the solution is just shown in this graph, in this graph. And for the first pair of antenna, which is these two things, this is the transmitting antenna and this is the receiving antenna. If we have the TOF of the transmitted signal, we could draw an ellipse. And we know the target should move around the ellipse, the first ellipse, the green one. And if we have another different pair of antenna and we have another different TOF, we could draw another different ellipse, which is the blue one. And we know the target should at the intersection of these two ellipses. And the final part is the simulation result by MATLAB. And this is our room, which is 10 meters times 10 meters room. And we let the person move from the point 19 to the point 82 linearly with speed 1 meters per second. And we could see the performance of our system is pretty good. And that's all of my presentation. Thank you.
Excellent, excellent. Thank you, John. So do you have any questions? He's located everybody in this room. He knows exactly where you are. This building is too big.
Okay, so how would you differentiate like different movements? Like for example, you said you can point at the TV and switch it on, right? So how would you differentiate between just a regular hand movement and movement that's directed to switch on the TV?
Because you mean the future applications for the smart house, right?
Yeah.
Yeah, it's actually it's enhanced system because if we could track the movement of the person, if we enhance our system, and it is possible that we could track the motion of like the hands. For example, if you point out that your hands to the TV, and the system can detect such motion, and then turn on TV for you automatically. But for now, my simulation is just for the movement of the person, like the person moves from there to there. Yeah, that's possible.
Okay, and then time for our questions. We have one over here.
Hi. So you're using an FMCW waveform
Yeah.
for the thread.
Yes.
So did you analyze the trade-off between the sleep time and the bandwidth of the waveform that you're using?
You mean what is the bandwidth of the FMCW?
There will be some sort of ambiguity if you consider it as a time frequency delay. So did you analyze what happens if you increase the bandwidth or increase the sleep duration or vice versa?
I'm sorry, I don't understand your question, so it's
Okay, so you have a certain sleep duration, right?
yeah.
So the sleep duration is definitely set bigger than the time of flight.
Yes, the frequency is much bigger than one.
That's a lot of combinations. And also you have a certain bandwidth in your sleep signal.
Oh yeah.
So my question is, did you study the trade-off between the sleep duration and the bandwidth of your transmit signal?
Because we use this FMCW why we use this FMCW, because it's the distance between the target and the antenna is pretty short, so the delay between the transmitted signal and the reflected signal is more in time domain. And for FMCW, the frequency changes with time goes by. So therefore, we try to transport this question to in time domain to this problem in time domain to the frequency domain.
Okay, so let me rephrase my question. Are you interested in tracking only of a single object or multiple objects?
Just a single one, because for now in our system, it's only can be it's possible to track the single person, but if there's multiple person in room, it's not impossible. It's impossible. Yeah. But you can use MIMO techniques to track the multiple person. Yeah.
Any other questions? Okay, all right. We'll let you,
Thank you very much.
yes, do we have a round of applause?
Hello.
Okay, next we have Arturex de la Cruz, and he's going to talk about rogue waves in a two-level pattern.
Hi everybody. My supervisor, Dr. Marion, and I'm going to be talking about rogue wave in two-level pattern. Medium, my bad, I missed that. And first of all, I want to explain what's a rogue wave. Imagine you're in the sea, you have a distribution, linear distribution of the height of the wave, some value, and suddenly, sometimes, the wave is going to show the wave huge, big, huge, high, 20 times higher than the median distribution, and of course, that's really dangerous for navigation and for the commercial ships. And we don't know what's happening, why this kind of wave occurs. And we know that, for example, the sinusoidal wave is represented or can be studied by linear theory of wave. But this kind of wave can be explained from the point of view of the nonlinear theory. And when that happens, the worst thing is not the height of the wave, it's the shape. Because the shape is some way that is it's called breaking wave. It means that all the energy is transferred to like a force, and when that hit, for example, a chip, destroy. Why destroy? Because the amount of force each square from this kind of low wave is around 100 tons each square, while the chips are designed for only 12, support only 12 tons per each square. I mean, you can see that why it's pretty dangerous. But we don't know, and the problem also is that those waves show up in the Pacific, the Atlantic, and there's no way to study the kind of wave. That's why the answer is right there, is optics, because when we have the experimental and setup, control setup, we can tune the parameter, we can do 100,000 simulations, and since it's a statistics problem, we can get the parameter of the simulation and try to explain what's happening. And my job is to study in this level atom approximation, how that behaves, and to see if we can control and determine when this kind of wave appears in for example, in fiber optics. Okay. That's all. Thank you.
Excellent, excellent. So, do we have any questions?
Thank you for your presentation. The root wave is a very important problem in the ocean of science. So what is the similarity between oceanic root waves and
the similarity of, for example, they don't, the brother rock wave, if, for example, you have a linear wave, or the sinusoidal wave, all the wave, those kind of waves, what they do is they suck energy from the neighbors, near neighbors, and then you see a big depression, and then a high, big high, and that's what's happening in all the systems.
So is there any similarity in the theoretical framework?
Yeah, they are described by the same equation, the nonlinear Schrodinger equation. It has a solution of that way. I didn't want to go so technical in that sense.
All right, any other questions?
Can you, in layman's terms, explain the cause of this roadway?
We don't know what's the more accepted theory is that they steam energy, because they are not linear wave, they are unstable wave, and then when they get unstable, they drag energy from the neighbors, from the other wave. But that's what we know. It's a statistical problem. That's why we have to do the simulation and experiment. But the physical, deep, we don't know. We thought about the resonance at the beginning. No, there's no resonance.
Any other questions? Last call. All right, well, let's have a round of applause. So, next up, we have Wang Pen.
Yes.
Okay, So this is Wen Pen, and she's doing a presentation on magnetically coupled resonance, wireless power transfer for small electronic devices.
Okay, good afternoon, everyone. My name is Wan. I'm from Microwave Wireless Research Lab, and my research topic is wireless power transfer, WPT for short. That is to transfer electric power without any physical connection. And this topic has been developed over the past few decades using various methods. And in my study, I used the methods called magnetically coupled resonance, MCR for short. And the schematic is presented here. It consists of 4 components: source loop, which is also driving loop, and transmitting and receiving coils, which acted as a high quality factor LC resonators, and a load coil. When the system has been properly designed, the energy is inductively coupled from a driving loop to the transmitting resonator coil, and then coupled to the receiving resonator coil via magnetic resonance, so that the energy is transmitted from the transmitter to the receiver. And here, in my structure, I put the transmitting resonator and source loop on the same side of an FR4 substrate, as well as the receiving resonator and load loop. The size of substrate is 32 and 32 millimeters, which is small enough to be implanted to our mobile phones. And the system consists 2 of these circuits. One is transmitter, another one is receiver. And in addition, for the receiver, the metal material has been added, which is the blue things on the figure, to concentrate the magnetic field. And also a slit ground, which is the green plane, has a cross slot on it, has been added, also to improve its performance. And then we can move to the last column, which is the results. From testing the S parameters, we can see the performance of the system. The top figure is the magnetic field distribution around the transmitting and receiving circuits. The left curve is S11, the peak is resonant point, and the right curve is S21. From the figure, we can tell that this system operates at the frequency 16.5 megahertz, and the maximum transmission efficiency is tested by the peak of S21, equal to minus 4.2 dB. That is 38% converted to percentage. And the maximum value occurs at the optimum transmission distance, 10 millimeters. To summarize, the work that I've done has a significant application perspective. It will hugely change the way of charging in the future, provides a mobile, safe, and more convenient solution to recharge the batteries of small electronic and medical devices. Thank you very much.
Thank you very much. So do we have any questions now? There's no power in this room, so we could all recharge our cell phones right now. That's great.
Thank you for your presentation. I have a question about the metamaterial which you use to concentrate and informing the magnetic inductive field. How did you design, or do you have any implementation of this metamaterial? And excuse me, another question. And did you observe or have a measurement on your magnetic field after the metamaterial, if there is any distortion or any does your frequency change, or have distortion after the metamaterial?
Okay, so for the first question, The metamaterial actually is based on the previous research results because this topic has been developed for many years and many structures come out. So I choose one of the material which is which has the best performance. And for the frequency, yes, it will change a little bit because the inductance will change. But just a little bit, it won't influence much for the results. Does that make sense?
Okay, other questions?
Hi, what makes your design different from the existent commercialized products? And the second question is, you're talking about wireless charge for cell phone. Nowadays, the cell of the cell phone is pretty much made with aluminum. Can you still use this kind of charging transmission through the cell phone case?
Okay, so because the point in my study is to make the structure applicable in the small electronic devices, so that's the point that my design has more advantages than others products that already have. And the other thing is that you're right, for the mobile phones in real life, there are many metal materials. I already test the structure that could couple metal above or something like that. It's applicable when it has the metal above or nearby.
Another question. What is the range of power you can transmit using this wireless? Does it also does the value of power in terms of
You mean the distance?
distance, frequency, operating frequency, all this stuff? I mean the value of power which was
The frequency range.
yes, it should change those parameters.
I just want to make sure I got the proper.
The value of power from the transmitter to the receiver.
The band of power. You mean the transmission efficiency?
That's transmission efficiency.
Yes, the 38% is the transmission.
We want to say that, I don't know, you're sending 2 volts. Does it differ if you send like 3 volts? So, different powers.
Different powers?
Yes.
What kind of different powers?
You can send transmit 2 volts, or 3 volts, 4 volts.
You mean multi-charge, like multi-charge. I'm not stepping to that process because right now I just use 2 ports network, 1 to 1, 1 point to 1 point.
Okay.
Excellent, let's have a round of applause. Next up, we have Andrew Dobbin. Come on down.
Test.
Okay, so my name is Andrew Dobbin. My supervisor is Dr. John Francois Bousquet, and my topic is a reliable acoustic link in a multi-static sonar network. The objective of my project is to create a highly robust, covert acoustic communication link in an underwater environment. It is is described in the figure in the top left between the sonobuoy, which is colored red, sending a green signal to a friendly submarine, which is colored green. The use of such a communication link would be used to send need-to-know information to the friendly submarine of information within that sonar network, such as like the whereabouts of an enemy submarine. The challenges, however, of facing underwater acoustic communications is such that since the ocean is such a time-varying environment, you have a lot of changing multipath profiles and varying Doppler shifts, which can extremely distort your transmitting signal and overwhelm your receiver. In addition, you have varying sound speed profiles, which generally describes a change of sound speed underwater with ocean depth. This can cause your signal to bend as you're transmitting, and creates shadowing energy zones, which essentially means that if you place a receiver at a specific depth, there might be a spot where you're receiving no acoustic signal energy at all. So these need to be taken into consideration when developing a modulation scheme. So what I am proposing is essentially a robust chirp modulation scheme. So a chirp is a linear frequency modulating signal, and we chose this because of its inherent wideband frequency. It is very prominent and very resilient in Doppler heavy environments, such as the underwater acoustic channel. With this chirp signal, combined with a frequency hopping spread spectrum technique and forward error correction codes, we hope to combat the multipath environment in the underwater channel, in addition to the Doppler effect. So with these both combined into one robust modulation scheme, we hope to get a highly reliable, low data rate. That's kind of the disadvantage. So low data rate but highly reliable communication link. And we plan on testing this in St. Margaret's Bay. You can see it in the bottom right map. We're going to be varying our ranges from 200 meters to 10 kilometers, and the expected results will be data throughput on the order of tens bits per second, but highly reliable and robust. Thanks.
Excellent, excellent. So do we have any questions for Andrew? I've got one way up here.
Are you the first one to work on coveted chirp modulations with chirp hopping patterns? There is some work before done on this.
There's other work that has been done on this. However, I haven't seen many done with chirp signal. So using a chirp signaling in addition to an OFDM or frequency hopping spread spectrum should be able to increase the reliability of such a network.
Why do you think frequency hopping is an idea to apply in this scenario?
So what we're actually doing, we're actually looking at various modulation schemes. So frequency hopping, spread spectrum is just one of the ideas that we're looking into. Typically it was used, the pseudo-random sequence that you choose for frequency hopping spectrum can be used to mitigate multipath. If your sequence, if the duration of your sequence is longer than your multipath profile, you can use that as a mitigation tool. But we're also looking into other techniques, such as employing a guard inflow, for example.
We have lots of time for other questions.
It's probably for my education. What is the most challenging issues in the acoustic links or in underwater network?
So I think particularly in this case, it will be the multipath profile. So in different underwater environments, you have very multipath profiles. So in shallow water compared to like deep ocean environments. And since the speed of sound underwater is such slowly propagating, these multipath profiles or echoes come in much later than they would in an FM system. So I think that would be
Would the delay be an issue too?
the delay, yes.
Yeah. Because they arrive at different times.
That's right. Yeah. And so it will cause intersymbol interference.
Any other questions? All right, thank you very much. Let's have a round of applause. Next up, we have Zahara Zanat. And I practiced this, but I didn't do it good enough. Okay, so she is going to speak on the mitigation of intercarrier interference for overtime varying underwater acoustic channels. Who has any questions? Any questions? I'm sure everyone wants to know.
There is a question.
There we are.
Please explain the curves which you have in your code. What channel do you consider?
Okay. This is a noisy channel plus with multipath channel. We have several paths with delays. And also we have Doppler effect for cellular Doppler scenarios. We tested the channel. And then this is the result that we got. We completely remove the ICI effect.
So you can remove the ICI effect?
Yes.
Is this a difficult channel from ICI perspective?
Yes, for example, with alpha equals 5, this is an extremely distorting channel, and we have a massive intercarrier interference in our system.
Okay, we have lots of time for other questions. Dr. Chen.
So what bandwidth you're talking about underwater?
Bandwidth?
Bandwidth.
Okay, we are using the frequency 1,723 hertz.
And what's the bandwidth you are going back? Bandwidth, not frequency.
Okay, this is the twice of this frequency. So we have like, I'm not sure about the exact number, but it is around 3,400 hertz.
3,000 and the carrier frequency is the
It
same?
is in baseband.
Baseband?
Yes. We consider this in the baseband, and then we will consider the future work in higher frequencies.
Because acoustic maybe is around kilohertz, right?
Yes, this is in base. This results in baseband, and we will add bandpass in the future.
So, no, I just wonder, it's a basement simulation, so you don't consider anything about underwater properties, medium property. And
We consider the delays, which is the result of multipath, and also the Doppler effect.
Okay, let's have a round of applause. Next up, we have Nisag Patel. Okay, his presentation is on path planning using genetic algorithms.
Hello, good afternoon everyone. My project is path planning using genetic algorithm, and before I get into technicality of genetic algorithm, allow me to introduce the idea of evolution using example of humans, for example. And first of all, we need a population, and let's say baby boomers, and alpha males and females get to reproduce and make new offspring, let's say millennials. And those millennials, they get their qualities from both their parents. So we can say that they are smarter, more intelligent, although baby boomers might disagree with that. But that's how we evolve as humans for better quality according to our environment. And the same concept can be used for genetic algorithm. So right in the middle, I have the flowchart of typical genetic algorithm. The process starts with an initialization of population. So in this step, we, in the case of path planning, each path is an individual. So if there are 100 ways to get from point A to B, each path is an individual, and that's our generation of 100 paths. Next is fitness evaluation, where we assign cost to each of those paths. In our case, it's the distance from start to goal. And if it passes through an obstacle, then I introduce a penalty of 1,000 points. So that makes it biased towards paths that don't cross over obstacles. Next up is checking if optimization criteria is met. The criteria could be number of iterations, which we call generations in genetic algorithm. Or it could be the time limit. If the criteria is met, then we stop the algorithm and return the path with least fitness as the solution. If not, we apply operators to the population. The operators can be crossover, mutation, selection. Crossover is when we have two different paths, we combine them to make a third new path. Mutation is when we have one path, we change one turning point, and we have a new path. And selection is the operator that decides which path gets to reproduce the third path, or which path is the mutated path. After the operators are applied, we have a new generation because there are operations performed on each of those paths from previous generation. This new generation is again evaluated, values are assigned, and then we check the optimization criteria again. And finally, when the criteria is met, the generation limit is reached, we have the final path, which is probably the shortest, but not necessarily, but optimal answer. And that's all from me. Thank you very much.
Excellent. So now it's question time. Who has some questions? We have questions over here. I should take a camera and take a picture just to make you nervous.
So I have a couple of questions.
Yeah.
Actually. So are you using linear genetic programming or are you using neural networks?
No, I'm just using linear. Like G is the only part of this.
Okay, and what's your objective? What have you defined as the objective?
The objective is to find the shortest path, but the main thing that I'm trying to minimize is the computation time. So there are many traditional algorithms that we can use that will make sure necessarily give us the shortest path, but it takes so much time. So it's a compromise I'm willing to make to save the time, save the computation time.
And how do you introduce diversity in this?
How do I introduce diversity? So in the initialization of population, I don't discriminate between feasible and infeasible path. I take all the paths. So that allows me to choose infeasible paths that can turn into feasible paths just by, let's say there's a path that is good for the most part and just near the end it just goes through obstacles just by a little bit. And I consider that path as a possible potential solution. So in between, somewhere in the iterations, mutation might happen and that path can turn into a potential solution. Right.
You're not really multiple objectives. So if you're using only one objective, wouldn't you, through your evolution, search for only the fittest?
Only the feasible solutions.
So how do you maintain diversity in the gene pool?
Right. So if I use only the feasible paths, then the question of diversity, because there might be a path that could be a potential path, but I'm just canceling that path just because it is, as of now, not feasible. So I'm not. So I'm using rank selection. So I'm not just eliminating the paths that are infeasible and considering keeping them in the pool. So with mutation, chances are that that path might become feasible in the next generation.
So you mean you're not throwing away the
Yeah, I'm not. Yeah.
Can you give me the parameters of your optimization?
So
I mean the population size, the number of iterations.
So for my simulation, so it depends on depending on the map and application, it changes. For my simulations, I used 20 generations, and 100 paths as an initial population. But first I wrote the code twice, one using MATLAB functions and one using line. And in the MATLAB functions, it converged around 15th to 20th generation, and with line code, it converged around 12th.
And what is the dimension of this problem?
So I'm using 512 by 512 pixel image. So I'm just...
No, the objective functions, the dimensions of the objective function.
Oh, objective fitness function, you mean?
The number of independent variables.
Oh, the number of, it's just, so for me it's 2. And those 2 are the intermediate points that I'm taking. So that value can be changed. For example, between start and goal, I can choose 5 intermediate points that the algorithm can choose. So in that case, the intermediate points would be 5. So 5 independent variables.
Thank you for your presentation. So as we know, genetic algorithm is among semi-heuristic algorithms. It means that we may fall into local optimum answer. So we usually consider some seeds and we solve for different seeds. And usually calculate the probability of falling into local optimum. So did you do anything like that? Did you do something that shows how probable it is that we fall into local optimum and we can get actual best answer?
Right, right. I have not done any calculations about how many times it has fallen into local optimum, but that is why I have introduced mutation. I have increased the probability to 40%. So the standard MATLAB probability of mutation is 20%, and I use 40%. And it gave me 2 seconds of advantage on the algorithm. Like convergence was 2 seconds faster. So for now, that improvement was only based on trial and error. I haven't done any calculations as to when it falls in local optimum or when it doesn't.
Thank you very much. Let's have a round of applause. Next up, we have Stephen Chandler.
Cool. That's this.
Okay, so now we have Stephen Chandler. He's going to speak on digital receiver using cyclic preference for frame detection and coarse Doppler offset estimation.
Imagine you're sitting on a boat on a calm day in the Gulf of St. Lawrence and you catch a fish. Your goal is to track a school of fish through the Gulf to determine next year's harvest quota. You attach a transmitter to the fish, hold it underwater, and listen for its location using the microphones trailing behind your boat. They pick up the fish's location, and so you let it swim away. A few seconds later, the signal is lost. So, why didn't this work? How can we fix this? My goal is to break down digital communications and organize it so when something doesn't work, we have the tools to understand why and an approach to fix it. For example, we know radios work. Communicating with sound underwater is more difficult than radio through the air. If we have a flexible radio design, we can use it as a base for testing underwater acoustic communications. I work with field programmable gate arrays, or FPGAs, which are a type of computational device. You program a computer with software, but you configure an FPGA with digital logic. You can use an FPGA to run a hardware design at full speed without the need to fabricate a chip. And this is fantastic for prototyping and research. The FPGA controls a software-defined radio which is a type of radio that can be configured to listen to FM as a Wi-Fi wireless router or even as part of a cell phone. The first thing we need to know about a signal is that it exists and at what time. This task is called synchronization. The main way to synchronize is to match part of a received signal with a known signal. Instead, I've explored repeating part of the signal at the transmitter and comparing these repeated parts at the receiver. This tells us when the frame has been received. Walking down the street, you may hear that an ambulance traveling towards you has a higher pitch than an ambulance traveling away from you. This change in pitch you hear is due to a physical effect called Doppler. The faster the ambulance travels towards you, the higher the pitch, and the faster it travels away, the lower the pitch. Doppler changes an underwater acoustic signal much more than a radio signal because the speed of radio is light speed, and that's 2,000 times the speed of sound underwater. It turns out that comparing the signal with itself also gives us some information about Doppler. We don't just want to talk to fish, but also with submarines, buoys, scuba divers, and a whole underwater network. Cracking the problem of underwater acoustic communication could lead to interesting applications we don't expect. Thanks.
Excellent, excellent. So, any questions for Stephen? Right here.
Thank you for your presentation. How do you want to cancel that Doppler effect with your FPGA? What is your goal, and how do you want to cancel it?
So, I'm working with a similar radio design to what Ali presented earlier that has pilot signals embedded. However, it's based in OFDM, orthogonal frequency division multiplexing, and the technique we typically use with OFDM is to include a cyclic prefix, which is where you copy the end of the frame of data you want to transmit and repeat it at the beginning as a prefix. So comparing these, the cyclic prefix with its tail data, we can find the difference between values, and this tells us almost directly the Doppler frequency.
In your calculation, is it important to consider the phase difference or the time delay? Because in FPGAs, usually ultra FPGAs use I think PLLs, and Xilinx usually uses DLL delay. So which brand you use, and why is that? Why are you using that brand?
So I'm working with the VC7 VC7 Vertex 7 Xilinx FPGA. It's a prototyping board and it uses the Vertex 7 FPGA. I mean, really, I'm working with it because it's what we have available. But it was, at the time, it was researched, it was one of the stronger versions. Yeah.
Yeah, but it has DLL inside it, and
DLA?
DLL, delay line,
delay lock loop.
And for this kind of calculation, casting the Doppler shift, I don't know whether PLL is more suitable for DLL. We investigate that because FPGAs use different clock managers and
Well, I haven't thought too much about that problem because for the most part I'm able to have the flexibility to do the calculations manually. So, I mean, when it comes to having an FPGA design work on its own, a lot of that is handled in synthesis and implementation, but the calculation itself is what does the work.
Any other questions? Okay, let's have a round of applause. Thank you. Next up, we have Hanang Purohit.
Hey guys, my name is McCain. My supervisor is Dr. Gu. I'm going to talk about ice mapping with unmanned aerial vehicle. So, in the Renaissance era, in the Renaissance era, when the European ships sailed across to find new trade routes, they stumbled upon a new world. This new world is called Western Hemisphere. The first thing that people did was to build a map of this new world. So the map is very important to finding new places. In robotics environment, it's also true that I'm going to talk about graph slam that I'm working on. There are many different techniques for slam. Based on EGF, particle filter, etc. The graph slam is based on a node in edges. So node is it says the position of the robot, like here X1, and landmarks are the distinct feature that can be easily distinguished from. It can be easily identified and distinguished. Like here, like in the map itself, like Morakemba building, you can take it as a landmark. One problem with landmark is called data association. Is that when robot goes to the unknown environment and build the map of the environment, when it again goes back to the places where it had seen before, it should be able to identify that I have been to this place before. So this can be done using nearest neighborhood approach or joint capability branch and ground. And if the SLAM approach can be solved, then it would be slam dunk for robotics. Thank you.
Excellent, excellent. So what do we have for questions? Do we have questions from the floor? Yes, we have one up here.
All right, so you are going to map the ice, and the ice is moving constantly with the currents.
Yes.
And also, you need to logistically make the drone capable of flying over the fields of ice without recharging the battery or getting more fuel. So
yes.
How are you going to organize it logistically? What's your approach to the fact that the ice maybe moves for many meters every day?
Yeah. The idea is like when you go on ocean water, the UAV is sent through from a ship. So the operation would be, for now, they are using the AR drone, which lasts like around 15 minutes with one operation itself. But if you have bigger capability on the unmanned aerial vehicle, then it can go on for an hour and it can map the ice and come back.
And what's the application, main application of this map? So why you are doing that, basically?
The bigger thing is to send UAV unmanned surface vehicle and unmanned underwater vehicle, and
and build the 3D map of the iceberg, so you can see the depth, how thick it is, and some other stuff.
Do we have other questions from the floor?
Yeah, it is regarding this UAV.
Yeah.
About the range of this UAV, because if you use it, for example, how long it will fly? For 20 minutes or
15 minutes.
15 minutes. How can you cover these things from the stations where it will be?
Right now we are doing it in simulation, and
because my question is, can you send that UAV to the locations that can take the pictures and return back within these 15 minutes?
yes. Like if you are sending it from ship, it can easily go for 15 minutes, take the, the surveillance area and come back, get charged, and go back to the next operation.
So if you have a ship there, then what the advantage is to use these things? Also, if you can scan it from the satellites, but it is like, what is the features of these techniques versus the existing techniques?
The satellites?
Yeah, satellite-based or by...
With satellite, you cannot have the same kind of resolution that you can have with on UAV. The sensor that you can put on an unmanned aerial vehicle and have a view which is very close to where the iceberg is. So, like you can put on infrared camera on that as well, and you can do a different kind of analysis.
Thank you.
Any other questions? Yes.
So, like, as he said, like, if the ice moves, and you said the drone is supposed to know that it mapped this location already. So if the ice moves, how would it recognize that it actually been there before?
Sorry?
If the ice does move, and the drone goes to the same spot, would it remap it, or would it like say that? Like, I don't know.
That's why, like, when robot goes to environment and maps the ice, it also knows where it is compared to the location of the ice itself. So when it comes back, it should recognize that, okay, I've seen this ice before.
Excellent. Well, let's have a round of applause for Hemang. And next up, we have Affluent, and he has a presentation. And Affluent's presentation is entitled The Ocean Ambient Noise Analysis for Single Carrier Communication Systems. When you're ready. Wait a second. The laser.
Good afternoon, everyone. My name is Al-Roomi, and I'm under the supervision of Dr. Buske. And today I'll be talking about ocean noise analysis for a single carrier communication system. First, let me talk about noise in electrical system and communication system and compare it to weed in farming. We all know that weed is unwanted, yet often there in our system, just like noise is often there in our systems as well. The first thing we have to think about is the sources which produce this noise, which can be classified into natural and artificial sources. And second, we have to think about how do we mitigate or reduce them in the communication system. The first thing I know about noise is that when we consider the ocean environment, the noise is random by nature, yet when it's observed over a time interval, we find there is a degree of resemblance between pairs of hydrophones deployed on the water, like the first picture there. And for all the pairs of hydrophone in an acoustic network, we find a degree of resemblance between the noise on the receivers. And next there we have to, because of the correlation there, we can extract a function which describes this correlation as the space-time correlation function. And next we have to think about the geometry and the noise field present on the water. And here, if you look at this very well, this is a receiver that lies just immediately beneath the ocean surface. And the noise that's on top, the angular radiation pattern, is higher in energy compared to the one that's reflected in the bottom. In this case as well, which is a shallow environment, we realize it's inhomogeneous because there's a lot of reflection from the bottom boundary. So we think about a mathematical model which represents this arrangement of arrays on the water, and the mathematical model here is the Green's function, which compares the noise field to the signal of noise in a closed loop. And next, I went a bit further in the research to do some validation and extracted the noise coherence in the picture you see here, and which will find that the red part represents the real part and the blue part represents the imaginary part. And I as well extracted the space-time correlation of the noise, as you see in the other picture there. And one cool thing we find about this is that even though noise is random, we can see that it's stable over a period of time, and as well it's just predictable. And because of this knowledge, I went ahead to put it into a communication system where I evaluated the performance for an uncoded QPSK link, and I determined the means to enhance the performance of the system. So I compared the mean squared error of the output of the decoder here, comparing the D with the S, and then a figure of merit used to evaluate the performance as the mean squared error here. And the output is taken for S in the time domain. And just like I said earlier, noise compared with read, even though it can be controlled, even though it's random and unwanted, it can be controlled. The same way noise in an underwater communication system can be controlled. Thank you.
Excellent, excellent. So now, all the good questions. Yes.
So first, I have a question about the sea trial. How was it organized, and where have you done in your experience?
Okay, so the sea trial was done by the team in the lab at the Halifax harbor. What we had was we deployed 2 hydrophones. First of all, we wanted to see which geometry is going to work best for correlation of noise. So we tried the horizontal collocation of hydrophones, and then we tried a vertical arrangement of hydrophones, in which we found that the vertical array gives us a longer coherence time compared to the horizontal array. So the setup we had was, we couldn't complete that quite, but the one we used here was we had 2 hydrophones that we connected to a laptop. It's kind of crude. We connected to the laptop and we used Audacity to extract the spectrum of noise that we see there. So we tested for surface noise, and we as well observed for a period of time when there was a passing ship. So we represent surface noise as well as distant shipping noise.
And then when you, for example, communicate how significant is the noise correlation versus the channel, knowledge of the channel itself, and the correlation, spatial correlation of the noise channel? What kind of signal-to-noise ratios are you expecting so that the noise will significantly affect your signal?
So the noise what?
What kind of signal-to-noise ratios are we talking about? So what's the importance of noise here compared to knowledge of the channel itself?
Well, the knowledge of the channel itself, we tend not to represent it in terms of the ambient noise. Like, I am not basically working with the channel here. I'm working with the ambient noise channel. So I think there is a different dynamic to it.
That's right, but why is it important to know the noise maybe the noise is 30 dB down from your signal. Maybe it doesn't matter how it's correlated. Why do you think it's important?
Well, the reason it's important is first because in underwater systems, noise, which has been proven in literature, is that hydrophones get swamped in noise from different sources. And as well, hydrophones themselves in literature is observed that they produce sounds which, when you observe it over length of time, is kind of noise-like in nature as well. And noise from maybe boats that we anchor hydrophones to sometime as well. So all of these, whether we like it or not, it tends to swamp our systems on the water. And that's why I think it's important we evaluate that.
Thank you.
We have another question in the back here.
So I'm just wondering how you distinguish the noise from the channel impulse response.
Well, first I will say that I am not working with the channel itself, like I said in the previous answer. I'm working with the ambient noise channel. And the characteristic of the ambient noise is, for us to understand the channel, we have to represent it in space and in time. And the math model, which I talked about, which is the Green's function, in itself is the impulse response of that noise channel. So there is a close similarity between the impulse response of the channel you're talking about, and as well the impulse response of the space-time ambient noise channel in this model.
Okay, so if we refer to the sea trials, if you can let me know what kind of signal was transmitted, it will be easier for me to understand.
Well, in the sea trial, all we were trying to do was just to listen. We didn't transmit any signal, as it were. So the reason I did that was just because I wanted to validate data over simulation.
So how much was your bandwidth?
Pardon me?
How much was the bandwidth?
The bandwidth we work with, because the one that we were given by the client is it's a narrowband 400 hertz, and the center is 2.4.
Okay, any other questions? Okay, so I think we should really put a big applause here for Avalon. And we also have to have a big applause for all these people that have presented, because they have to come down here and we're going to take some time to get their pictures. So all the 3-minute thesis participants, they could come to the front. We're going to get a group picture. And they're going to now tally all the numbers. And now the guys that are judges are going to actually figure out if they can do algebra. And we'll make all the announcements of the winners, the prizes, and trips to the Caribbean in 10 minutes.
عادي؟ عندك بعد المقطع مالتها خلها حين هنا 3 minutes. What?
Is our turtles up there? For the cruise? Aging. Our turtles didn't.
Okay.